Good morning and good afternoon, Canada, and good evening, depending where you are on the small planet. We are with you with another webinar in the series of Global Water Future thematic webinars. Our today webinar is on water quality theme and the achievement over the past year and the vision for the final year of GWF. The water quality team is focusing on three main tasks. The reanalysis of historical water quality data and trend, the development, benchmarking, and application of process-based and integrated nutrient models, as well as improvement of algorithms for simulating water quality at various scales. Our speaker today is Professor Hqp van Kapellen from University of Waterloo, who leads the GWF core model water quality team. We have set up this webinar in a slightly different format. Today, our panelists will also present their work. Mahyar Shafii and Sarah K. Khosravi from University of Waterloo and from University of Saskatchewan, Bafakado Voldegiorgis, Julie Terry, and Puya Sabukruhi. They will cover a range of topics as well as geographical domains. The presentation will take about 45 minutes, and we will have question and answer session after the presentation is over. As this is the last thematic webinar of 2021-2022 of the GWF core modeling, I would like to thank you for being with us. On behalf of the core modeling management and coordination team, Al Petroniro, Martin Clark, Joy Mitsugiani, and myself, Shelvan Arali. We wish you a happy summer vacation in advance. Philip, floor is yours. Please share your screen.
Thank you, Shelvan. Let me see. All right, can you see my screen?
Yes, perfect.
All right, so yes, hello everyone, and welcome to this webinar, which will review some of the advances in water quality modeling. So generally speaking, human-driven change in water quality have tended to negatively impact aquatic ecosystems, but they also, of course, affect human well-being, economic development, and public health. So to assess these impacts of water quality changes, we have to take into consideration a broad range of criteria. And we usually do that through an equally extensive range of physical, chemical, and biological variables and indicators. So this is just to emphasize that water quality is a broad concept. There's no unique definition, and it really varies depending on the lens through which you look at the water quality. So water quality are complex, but they also affect large portions of the world. And you can see that here on this figure by the many red areas that you find on the world map. In fact, the World Bank refers to this as the invisible water crisis. And that's in contrast to, say, highly visible flooding events or severe droughts or changes in the water level in a lake. Now, note that the figure here is a risk map. So it really is a combination of the vulnerability of regional water resources to water quality deterioration, plus the population density, the level of socioeconomic development, and other factors, such including political factors, for instance. So as Shelvan already indicated, the format of today's presentation will deviate from the typical one-person review webinar. So I will be giving an approximately 12-minute kind of general overview of water quality modeling in the Global Water Futures program, illustrated by some examples. And then this will be followed by 3 presentations by HQPs from the core modeling team. And so that's intended to give you a flavor of the diversity of activities and water systems that are being addressed. And so I will come back to these 3 presentations at the end of my overview. So here's a list of the major thematic areas of water quality modeling in Global Water Futures. So we deal with soil and snowpack processes. Obviously, there's a focus on cold regions, hydrology, and chemistry. There's been some important work done on sediment transport modeling. Obviously, a lot of interest or a lot of focus on coupling hydrology and biogeochemistry, in particular the biogeochemistry of nutrients, the role of dams and reservoirs and legacies, and how those affect nutrient loadings to surface waters. In more recent years, also more emphasis on urban hydrology and water quality, Still a lot of work on coupling watersheds and loads from watersheds to lake impacts. And one of the big impacts that we're looking at is, of course, algal blooms, both in terms of understanding the controls on algal blooms, but then also in our ability to predict algal blooms or how they might evolve also over longer term as climate warming takes place. Sorry. So some of the key outcomes, and this is certainly not an exhaustive list of outcomes of the water quality modeling work in global water futures. So as I said, work on winter soil processes, for instance, quite some advances in our understanding and characterization of snowmelt chemistry and chemical fluxes, cold regions soil respiration, in particular during the winter, the effect of freeze-thaw cycles, for instance, on impact on fertilizer leaching. There's been quite some improvements in model functionalities and performance through coupling different models or model components together and also upgrading existing models. And so you have a whole list there of acronyms referring back to these models. There's been also comparative assessments of existing water quality models, so kind of the industry standards and seeing how they perform or how they diverge among each other. Obviously, a lot of work on catchment, sediment, nutrient, and contaminant loads. And you'll see some examples of that in my presentation and the Hqp presentations. Also the use now of artificial intelligence in using or making nutrient load estimations. And you'll see an example very briefly of an application for the Great Lakes basins and then urban stormwater nutrient export and mitigation. Continued work on dams and reservoirs, both in Saskatchewan. For instance, you'll see some work on Buffalo Pound Lake, and then also nutrient retention by dam reservoirs in the Great Lakes basins. Then work on nutrient legacies, because what we see today also depends on what we did in the past. And so lots of work on agricultural nitrogen and phosphorus legacies, but also legacies under the form of phosphorus in lake sediments and leading to what's called internal loading. And then finally, a lot of work on trying to understand lake eutrophication and ultimately also predicting lake eutrophication. So in this slide, I've tried to summarize the timescales that are being addressed by the modeling activities. Note that these timescales here do not necessarily indicate the temporal resolution of the modeling tools, but rather the typical temporal ranges of the model applications. And so at the shorter timescales, we have, and we are continuing to develop model capabilities to simulate and predict the behavior of highly dynamic processes and systems, such as the hydrological and biogeochemical connectivity in small agricultural catchments or streams in mountainous areas, as well as the daily to monthly forecasting of algal blooms in lakes. The work on watershed nutrient and sediment loads goes from daily to annual prediction, while most of the applications dealing with the effects of damming, reservoirs, urban stormwater management, and large lakes biogeochemical cycles fall in the seasonal to annual range. And then the work on nutrient legacies, both in watersheds and in lakes, and historical reconstructions based on sediment core data and modeling cover even longer timescales. So much of the efforts in model developments have focused on improving our ability to predict the concentrations and loads of the nutrients, nitrogen and phosphorus. And so one example on the what I would call the mechanistic modeling side has been the coupling of the cold regions hydrological model to biogeochemical modules that represent the sources, the forms, and the processes that control the fate and nitrogen and phosphorus in catchments. And so, for instance, this allows us to now much better account for the effects of, for example, snowfall and snowmelt that are, of course, very important in cold regions. Another application is more on the statistical model application, so the use of artificial intelligence approaches. And here, for instance, and sorry, the figures is fairly small, but it's actually illustrated here for phosphorus and nitrogen across the entire Great Lakes basin. So if you look at any one of these individual little plots, it represents the entire basins of the 5 great Laurentian Great Lakes. And so this is a random forest model that has been trained on an extensive data set on stream flow and phosphorus and nitrogen concentrations. So as also mentioned, we as a group, there's been a lot of work on watershed nutrient legacies, and that has continued using the element model, which stands for exploration of long-term nutrient trajectories, which was developed in Nandita Bazu's group. And so her group continues to apply this model to an increasing number of geographical locations. And so, for instance, recent applications have estimated the historical accumulation of nitrogen and phosphorus in the basin of the Grand River in Ontario. And so the figures on the right, for instance, show the different accumulation patterns of the two nutrient elements over the various compartments in the watershed. Now, if you just look at the lower right hand figure, you can see that the estimations for phosphorus go back to the start of the 20th century, when actually agriculture was introduced in the region. You can also see that most of the legacy phosphorus is now stored in soils. What I'm not showing is actually the use of the model also to predict how the slow release of this legacy P phosphorus will actually affect the phosphorus loads in the Grand River in the future under different management scenarios. Now, the key input to this element model is the net nutrient surplus to the landscape. So the inputs via manure, fertilizer, and domestic waste, minus then what is being removed via crop harvesting. And so the animation on the right shows the estimated yearly phosphorus surplus since the 1930s across the watershed of Lake Erie. And of course, what this very clearly illustrates is the very high degree of variability, both in time, but also spatially. So model applications are also helping to quantitatively understand the effects of dam on water quality, including the loads and speciation of nutrients. Here's an example of a dam reservoir in southern Ontario, which in fact, without going into the detail, shows a very strong seasonality and interannual variability of phosphorus retention by the dam reservoir. And the model that we're using actually can capture this variability. So that also opens the possibility of exploring how dam operations could be used to reduce phosphorus loads. And in one of the upcoming Hqp presentations, you will also see some work on water quality in Buffalo Pound Lake in Saskatchewan. Now, in a recent data mining study, 5,000 algal bloom events in 340 lakes at latitudes higher than 40 degrees north during the period 1964 to 2019 have been analyzed. And so the trends that we can then get out of the data inform us about the long-term drivers of changes in lake productivity, which in turn can be then included in model developments and scenarios. And again, I'm not going into the details here, but the results on the right show that the spring algal blooms are occurring early in the year. And that's not surprising, and that has been known. But what that the data also shows is how fast this is happening. And of course, this is a result of higher late winter temperatures and earlier ice breakup. The fall and the summer and fall blooms are unaffected by this. And so this is very much in line with observations for Lake Erie, for instance, where artificial intelligence algorithms are able to accurately reproduce near continuous chlorophyll A records, mainly based on, or mainly fed by winter ice cover information and hydrometeorological data. Now, phosphorus in Lake Erie has continued to be a major focus of the modeling efforts in Waterloo. And in particular, the work has shown a very important role of the shallow nearshore, the littoral zone in the transport, transformation, and burial of phosphorus. So what you see in this figure up here, the redder the color, the more you have an east to west flow velocity. And then when you have blue or green, it actually goes the other way. So what you see in Lake Erie, and obviously that has to do with hydrology, the water is moving from east to west, but it's mostly moving along the shores. And so what this means is, in fact, that the phosphorus is also, to a large degree, transported via along-shore currents. And so the bottom line is, of course, that in the models that we're developing, the littoral zone is modeled as a separate biogeochemical compartment. What we also find, and that might be more surprising, is that, for instance, the offshore waters can actually be a source of phosphorus to the nearshore waters. Now, another major outcome is the quantitative estimation of the importance of internal loading in Lake Erie's phosphorus budget. And so on average, what we find is that this internal loading represents nearly a quarter of the total loading to the water column. Further, we predict that the internal loading is actually increasing in importance. And that is driven by several processes that are actually related to climate warming. As a final example, we've also been working on the changes in lake phosphorus cycling brought about by urban development in watersheds. And the test site here is Lake Wilcox, which is now part of the Greater Toronto Metropolitan Area, but at the beginning of the 20th century was still entirely surrounded by forests. And so the forest land was first converted into agricultural land, And then urban development really took off after 1970. So most of the lake catchment, or 60% of the lake's catchment, is now urbanized. So what we've done is combine data from a dated sediment core with estimations of the inputs of phosphorus to the lake, plus lake model calculations to reconstruct the phosphorus cycle through time since the 1900s. So in other words, going to the agricultural phase, then the transition to an urban, and ultimately continued urbanization of the watershed. And so the panels on the right here show you three time snapshots. The top one corresponds to the agricultural phase of the watershed. The middle panel represents kind of the transition period from agricultural to urban watershed, and the lowest panel is essentially conditions today. And so one of the major outcomes of that is that, and I was not expected, is that urbanization has actually caused a very, very large drop in the external phosphorus loading to the lake. And in part, this was surprising because the lake still is remaining in a eutrophic state. There's still algal blooms in that lake. And so according to our model, this is in part because of the intensification of the internal loading, which in turn is related to increasing salinization and the use of road salt in the watershed. Now, as a team, we are having ongoing discussions of how to best focus our efforts in the year to come, but also to define important modeling avenues that we now see also for the post-global water futures era. And so here I've listed, I'm not going to go through those, but those are some of the topics we've been coming up to. And of course, input from anyone would be obviously greatly appreciated. But so now onto our Hqp presentations. And so what we'll first hear from Befeqadu, and he will tell us about his work on advancing the coupling of hydrology and biogeochemistry models. In other words, how can we make these models better? Next, we'll have Puya, who will present some of the work of Julie on Buffalo Pound Lake. She couldn't make it today, but that work is important because it also shows how we can inform the management of this very critical water supply source based on the model outcomes. And then Puya will also present his own work on sediment transport in the Athabasca River Basin. And then finally, Mayar will focus on phosphorus speciation, export, and load mitigation in urban watersheds, and he will report back on the work we're doing in the Toronto area, and his co-author here is Sarah, but Mayar will be giving the presentation. So with that, I would like Befeqadu to take over and present his work.
Okay, thank you, Philip. Can you see my screen?
Yes. If you can go into the presenter mode.
Okay, my name is Befeqadu. I'm a postdoctoral fellow working with Helen Bulge. And the work I'm going to present today is focused on biogeochemical modeling in the Red Assiniboine River Basin using a Hqp model. So my presentation has two parts. The first one focuses on identification and uncertainty quantification of biogeochemical models. And in the second part, I will talk about some process improvements, particularly numerical scheme improvement and its implication on biogeochemical modeling. So the work I'm going to present is largely focused on exploring methods to improve model identification and uncertainty quantification within the existing modeling framework. So regarding model identification, I compare two approaches. The first one being the predominant approach, whereby the hydrology is inferred first and the biogeochemical model is set up based on the best hydrological parameters. And this method, I call it sequential approach. And the second method is a joint approach, whereby the hydrological and biogeochemical model parameters are inferred jointly. So within the joint method, I make two comparisons based on the type of error models fitted to the biogeochemical model residuals, which is the total phosphorus load residuals in my case. The first one fits the total phosphorus load residuals with Gaussian distribution having a constant variance, and the second approach the total phosphorus residuals are fitted with Gaussian distribution, but variance expressed as a function of the total phosphorus simulation magnitude. So the comparison is mainly focused on parameter identifiability and prediction uncertainty comparison. Here I'm going to present the prediction uncertainty comparison only. So the sequential approach, as is shown on the top panel, is struggling to fit the low loads. The low load is overestimated when the joint method with Gaussian distribution having a constant variance is fitted to the total phosphorus model residuals. We even see worse prediction uncertainty, showing wide prediction bands for the low loads, even extending to negative total phosphorus loads. Whereas for the joint method, which fitters Gaussian distribution with a heteroscedastic variance, which means the variance expressed as a function of the total phosphorus magnitude, provides the lowest error spread score, which is an indication that it had a better predictive skill, and it also provided better goodness of fit measures compared to the three methods. So the message here is joint inference of hydrological and biogeochemical model parameters leads to more optimum biogeochemical calibration only when the right choice is made for the error model. Regarding the process improvements, actually the work I'm presenting here is limited to the improvement of the numerical scheme used to solve the hydrological fluxes, but there are other works in progress regarding changes being made to the source code for the biogeochemical processes. So the work that has been done is regarding improving the numerical scheme used to solve the hydrological fluxes in Hqp. Hqp uses operator splitting approach, whereby the differential equations used to represent the different fluxes are calculated sequentially from a simplicity of coding perspective. But that method is known to provide less accurate results. Therefore, I replaced this less accurate numerical scheme with a more robust implicit Euler method and compare the groundwater contribution simulated using both approaches. And the graph here shows that the default method that Hqp uses, shown on the left top panel, is providing very high contribution groundwater. So 98 to 99% of the stream flow is comprised of the base flow. Whereas when the robust numerical scheme is used instead of the sequential approach, we see a shift of the groundwater contribution toward this 60 to 80% of the stream flow. And when these two are compared with the literature value of the base flow index of the basin, clearly the model with improved numerical scheme is providing a better agreement. This is actually when the calibration is limited to the hydrology. So what would happen if we constrain the hydrological model calibration by the joint inference of the hydrological and biogeochemical model parameters? So in this case, the default method, which is shown here, still provides high groundwater contribution. We don't see much difference. It's still 98, 99% contributed from the base flow. But when the model with the better numerical scheme is used to run inference of both hydrological and biogeochemical model processes, we see a much more agreement of the groundwater simulation with the literature value of the basin. So the message from this comparison is, for a better flow path representation, we need to have a robust numerical scheme, and constraining the hydrological calibration with joint inference of hydrological and biogeochemical model parameters further improves the water quality, the groundwater contribution when a robust numerical scheme is used. So the question is, how would this translate into biogeochemical modeling? We have seen that the flow path has improved. What's the implication on the water quality modeling? Well, the results showed that the improvement of the flow path representation didn't directly translate into the biogeochemical model improvement, which suggests the need to reconceptualize the biogeochemical process to make use of the improvements that have been obtained regarding the water balance of the hydrological model. A couple of works in progress is regarding improving the adsorption-desorption processes in Hqp concerning the phosphorus modeling. And another work in progress is investigation of nutrient management scenarios in the Red Assiniboine River Basin. With this, I end my presentation, and I would be happy to take questions at the end of the presentations. Thank you.
Thank you very much, Befeqadu. Please unshare. And so the next presentation is done by Puya. Puya, if you can share your screen, please go ahead. You might need to unmute. Puya, please unmute yourself.
Okay. Hi, everyone. My name is Puya Salaflukia. I am here to present my research work, also the research work of Julie Terry, which was not able to present today. So as an introduction, Julie and I both are working in the western provinces of Saskatchewan and Alberta, and we've been both looking at how two or more water quality models can be coupled together to model the transport and fate of sediments, toxicant, and nutrients. And here you can see a study map of the map area of which Julie is studying. Julie is working in the upper Hqp River Basin, modeling the from Lake Diefenbaker to the Buffalo Pond Lake. And these two are most important water supply reservoir in the province of Saskatchewan, providing water to many population in the province. And this stretch will be extended further east down to the Hqp River in the next step of the project. So to give some background about the project Julie is working on, Buffalo Pond, as I mentioned, supplies the drinking water for around 25% of the Saskatchewan population. But as you can see on the map, the main inflows are managed water transfers from Lake Diefenbaker, but during flood event, it also receives some large amount of poor water quality from the watershed. So the lake management agencies want to increase the amount of water receiving from Lake Diefenbaker to the Buffalo Pond, partly due to the growth in the population and also the higher evaporation they are seeing. But, and to mention, Lake Diefenbaker gets its water from Rocky Mountains with good water quality. However, the water coming from the watershed doesn't have that good water quality. And so the goal is here to get more water from the Lake Diefenbaker. But there is an issue, and the issue is that because the landscape is very flat and the river channel has a limited capacity, so they should be very careful about the timing and the strategies of releasing this water, because it can lead to flooding. So Julie has been modeling different flow scenarios, and she found out, depending on the timing of the water transfer, mean concentration of nutrients in Buffalo Pond can decrease substantially over the simulation periods. The example plot that you can hear shows the total nitrogen. And this result has been also published for any of the audience who is interested in. Okay. So what Julie is currently doing is she's trying to improve how to estimate the nutrient transformation in the water diversions between Lake Diefenbaker and Buffalo Pond Lake, which is approximately 100 kilometers. And to do this, the modeling approach is doing is coupling a 1D WASP river model to an existing 2D C-equal reservoir model for a time period of 6.5 years. The output, so the coupling works in a way the output from WASP are being used as the boundary condition for the C-equal model. And both models has been calibrated. And the graph here is showing the calibration for the time period that I mentioned. And the end users and data providers, as you can see, Julie is working with both Saskatchewan Water Security Agency and the Buffalo Pond Water Treatment Corporation to develop the most relevant for their operation strategies. And both agencies are providing her with all the data that she needs for the modeling purpose. And also her scenarios will look at both flow management and climate change later. So this was the research work of Julie. And after that, I'm presenting my own work. So my study region is in province of Alberta, Lower Athabasca region. So, and the modeling approach I'm using is a mesh set coupling with a WASP. So mesh set is also a loose model of mesh and set, and it's physically based watershed sediment transport model. WASP is the finite difference model for analyzing the transport and fate of sediment and toxicant. So for my work, I'm modeling mainly sediment and also some heavy metals, including vanadium, which I'm going to discuss. So at the beginning, the mesh set model was developed, and for the time period that you can see, it is calibrated and validated. And we also have seen like a good NSE values, which shows that the mesh set model is acceptable, and we are ready to couple it with the WASP model. So for the WASP model, we had a quasi 2D approach. So basically, normal 2D approach was taking pretty long time on the previous modelers that try to model this stretch. So we come up with an idea to model this stretch with like a quasi 2D model. And here you can see how our segmentation and how our mapping worked. And also here we have a longitudinal profiles of our TSS concentration for the also with, which includes the observed values, and you can see our results are in like good values. And also we modeled vanadium. So basically the location that we're modeling, it has some oil sand mining industrial sites. So basically what we did and what was our goal was to find out the amount of the load from the industrial sites that coming to the stretch. And we were able to account for the amount of load that probably coming from the industrial sites to the stretch that we're studying. And here also you can see the longitudinal profiles. And as you can see, we've seen an increase, probably because of the industrial sites at the location. Will be answer any question at the end. Thank you.
Thank you very much, Ria. So now we'll turn it over to Mayar.
Thank you, Philippe. Are you able to see my slides here?
Yes.
Great, thank you. Hello, everyone. So pleased to be here giving this talk about the work that we have done in the past couple of years. I'm presenting on behalf of myself, Sarah, and other team members at University of Waterloo, led by Philippe. And special thanks to our partners in the project, especially CBC, TRCA, and City of Richmond Hill, who helped us with the field setup, sampling, and they provided us with data used in our work. So our work is on urban phosphorus, mainly on speciation, export, and assessment of nutrient control measures or load mitigation options, in urban landscapes. Just to give you a bit of context, we know that urbanization and imperviousness has impact on water quantity and quality, and our focus is on phosphorus, which is just a major nutrient driving eutrophication-related issues in freshwater ecosystems. Among characteristics in urban landscape that affect phosphorus export is flashy storms, higher flow peaks in urban catchments compared with rural and natural areas that results in a large fraction of annual loads being exported within a small number of large events. So when it comes to modeling the systems, we have to be able to replicate this pattern. There's also a variety of stormwater control measures, including gray infrastructure like stormwater ponds and green options like bioretention that I'm going to explain a bit later. So these have effect on phosphorus cycling and speciation of phosphorus within urban landscapes. However, when it comes to modeling urban phosphorus, a little attention is actually focused on different phosphorus species. As a result, the questions that drive our work is how much actually urban phosphorus load is being exported via stormwater runoff? And are these stormwater control measures actually in a sink of phosphorus? And if they are, what are the main retention mechanisms in them? So today, I'm going to just overview briefly some of the urban modeling work that we have done in the group, and our focus is on speciation, as mentioned before. And the reason is that not all phosphorus forms are bioavailable and concerning. And also, aggregating everything into total phosphorus might not be as informative for stakeholders. That's why, we are just doing this project. Our study sites include 3 urban catchments, or called watersheds, in Ontario, 1 small residential watershed in Richmond Hill, and 2 mixed land use larger watersheds in Ajax. I'm going to call them Richmond Hill, Ajax East, and Ajax West in my talk. We also study a stormwater pond in Richmond Hill that receives drainage from the watershed mentioned above, and also a bioretention facility in Mississauga. And bioretention is basically a pit that is filled with gravel, soil, and some vegetation on top to enhance groundwater recharge and filtration of pollutants within soil media. So we developed a range of models in this project. Without getting into details, I'm just going to list them just in the order of catchment scale to plot scale. First, we have multiple linear regression models to forecast long-term phosphorus export in our study watersheds. We use monitoring data and climatic variables as predictors to extend model predictions to the past and potentially to other watersheds that have similar characteristics. We also use SWIM and adapted its wash-up process to, based on our monitoring data, to make predictions about different forms of phosphorus in urban watersheds using SWIM, which is just a novelty of that part. We conducted mass balance modeling in the stormwater pond using our measured flow and concentrations to estimate fluxes of phosphorus coming in, staying in the pond, and leaving the system. And the idea is just to assess pond's phosphorus retention performance. A process-based phosphorus reactive transport model was also developed for the bioretention cell in Mississauga to characterize the fate and transport of phosphorus within the cell and understand the role of different processes in the context of phosphorus cycling in the facility. So some results, our statistical models showed some seasonality in the export of phosphorus. For example, we see that fall is when a large fraction of annual loads, both for total phosphorus and dissolved reactive phosphorus, which is the readily bioavailable form, happen. Also, spring was just the hot moment for the export of the RP, that reactive component, the reactive form of phosphorus in Ajax West, which is the most green and one of the older storesheds among our set. We also see that unlike Ajax East and West, total phosphorus was exported evenly across seasons in Richmond Hill, which is just a young residential storeshed. Our SWIM results showed some variations across catchments. We see that even though the surface area of Ajax East is only 30% higher than Ajax West, and they are parallel sewer sheds in the area, the loadings that are exported in Ajax East are 2 times, 3 times higher. We also see that less than 10% of loadings in these sewer sheds are in dissolved reactive form, which is just a readily bioavailable one. However, if you look at the particulate phosphorus pool, we see that there is 40% bioavailability, in that pool. So these sewer sheds overall export lots of particulate phosphorus, and that 40% fraction of bioavailable is not something that we can actually neglect. So our mass balance showed that pond is a great sink of phosphorus in this area. We have up to 70% retention of different forms of phosphorus, mostly through sedimentation in the bottom sediments. And in order to understand what is behind this phosphorus retention and to see what forms of phosphorus exist in the sediment, we actually did some laboratory experiments on the sediment cores taken from these cells. And we see that as water flows through the system from inlet to the outlet, the diffraction of reactive phosphorus pool, it actually decreases. So this means that this pond is transforming reactive phosphorus forms to non-reactive. And we see that if you look at the green light bars, the light green bars in the graph, that is the calcium-bound phosphorus pool, which is a really stable pool, and it's actually increasing down the core. So basically, this pond is retaining phosphorus and storing it in a stable pool, which is a great thing. And the calcium-bound phosphorus is actually formed by the formation of calcium phosphate phases. It needs high pH and calcium in the area. That was the case in this study site. And that's why we hypothesize that process is one important mechanism of phosphorus retention in this pond. When we look at the results of bioretention cell model, we see that soil accumulation is just the main mechanism behind phosphorus retention. You see the large piece in the left pie chart. And when we focus into the soil, we see that most of the accumulated phosphorus is in mineral, particulate inorganic, and stable particulate organic forms, those big pieces in the right pie chart, and they are quite stable. So this also means that this bioretention cell is doing a great job in terms of capturing and storing phosphorus in there. So what you see on the screen, these plots are something that can be provided to us by a model like the one we developed here, and just data cannot present the same thing. We also see that the top 10 centimeters of this cell has 30% higher concentrations than the bottom layers, but the bottom layers are not saturated that much from the phosphorus perspective. So basically, this cell is far from being saturated, and if just the top layer is replaced, we can actually have this cell going for another 10 years. This cell has been functioning for 10 to 11 years so far, and we can still have this cell functioning. And so the model result has some implications about the life cycle of this option. So in terms of implications, the models that we have developed can be actually used as decision support system. So we can provide those load estimation models to stakeholders. They can use it to determine the subcatchments that are not gauged, but there is a risk of high and elevated phosphorus export in them. We can also use the bioretention cell model to test different designs of bioretention. We saw, for example, that if we remove the plant optic, if you remove vegetation from top, the loadings in the outlet would be 2 times higher, still much lower than the inlet, but 2 times higher than when there's no vegetation. That implies that this vegetation layer is really important. So we see a large amount of particulate phosphorus being exported from urban catchments, and there's a significant potential of bioavailability. So that is something which is underappreciated when it comes to nutrient control in urban landscapes. We also see that our stormwater control measures, the one that we studied here, are a great tool for load mitigation. There is transformations from reactive to less reactive phosphorus. There is storage in the stable phosphorus pool through chemical processes. And these are the things that the insight or information that can provide it to us by phosphorus speciation analysis and modeling. I have to note that, that chemical process, formation of calcium phosphate phases, need high pH and calcium. So we have those situation available in the site, but maybe they're not as high in other sites. So that's something that we have to take into account. Overall, we try to make a case for phosphorus speciation as a method to give us better insight into cycling of phosphorus within urban landscapes. So our ongoing and future work, we are developing a process-based model for the pond, something similar to the bioretention cell, to get the same level of insight into phosphorus cycling. We're also analyzing existing large databases of urban watersheds and best management practices to see if we can actually generalize our findings to other systems. Are these BMPs or the stormwater control measures that sink of phosphorus all the time, or there are situations in which these cells become a source of phosphorus? And we're also upscaling the soil model from the watersheds that we studied to the northern shore of Lake Ontario to quantify the amount of loading that actually get into Lake Ontario from urban landscapes. So with that, I would like to end the talk and ready to take questions. Thank you.
Thank you very much, Maya. So I can now turn it over back to Shervan to see if there's questions.
Yeah, thank you very much for your presentation. Very interesting insight into what's going on. Water quality team. We have basically 10 minutes to the top of the hour to cover some of the perhaps questions. We have a question in the chat from Mazda Kompanizare, Puya, for Puya. Puya, very good presentation. I was wondering why you use quasi 2D and divide the system longitudinally to 2 parts. Does it mean the water don't have enough time to be mixed?
Yep. Thanks for the question. So it's a very good question. So basically, why we did the quasi 2D, it was the mixing was taking some time. What we approximated was around 50 kilometers, and that's the stretch we modeled. So basically, water was coming from 2 sides, one main Athabasca side, and also another side was clear water. So the one from Athabasca side was more turbid, so they were pretty different characteristics they had. So, and it was taking around 50 kilometers to mix. So that's the main reason we applied this approach.
Thank you very much. I don't see any other question. Yeah, as I said, thank you, Al. Yeah, excellent presentation and progress. Thanks, Philip, for organizing and great session, and to all the speakers. Thank you, Al. I have a question myself for maybe Mahia. Perhaps it's a long time that I didn't really work on water quality as such, and I don't remember all the chemistry behind it. But you mentioned that having some sort of calcium in the system will change the phosphorus into basically it retained the phosphorus into a way that it's doesn't participate in on the basically negative effect that it can have on the like algal bloom, etc. If I'm correct, sorry if my question is a little bit late, but is there any possibility, what's the order of magnitude? Can those chemicals or like calcium, whatever is that, be added to the system so that it basically prevent or capture all this phosphorus? I mean, maybe it's probably tons of like mass, or maybe it's not. What's the magnitude? Is that possible even?
Mm-hmm. No, thank you. That's a great question, and I think a $1 million question. When it comes to using them actually in practice, right? So I just provide my 2 cents on this, and then maybe give the floor to Philippe, who is the expert in chemistry. But what we see in these systems is that something like that is happening, right? So, and from the top layer, at the high level, you don't see something like that when you just do a regular monitoring of these watersheds, taking water samples and sediment and just getting to know how much total phosphorus there is in there, right? And the lab method that we have, gets us the insight into whether or not a particular chemical process is happening, right? And we're seeing that it is happening based on just looking at the pool, the increase in the calcium-bound phosphorus pool. However, relatively, it's still physical process. Something like sedimentation is the major mechanism of phosphorus retention in a stormwater pond. But whether or not we can intensify that chemical process occurrence, that's something that we have to look into. I think Philippe has an example of using a practice like that elsewhere for phosphorus retention. Philippe?
Yeah.
Yeah, so to just add a little bit to what Maya was saying. So yes, the particulate phosphorus that comes in, a lot of it is actually under organic forms. And so when they get deposited at the bottom of a pond or a lake or a stream bed, that organic matter is being degraded and the phosphorus is being released. And in particular, you can have times of stratification, even in shallow ponds, where the bottom layer becomes anoxic, and that then stimulates the release of the phosphorus. So that's this process of internal loading that I was also talking about. But if you have a process like the one we see in the Richmond Hill pond, the phosphate that's being released from, sorry, the degradation of the organic carbon is actually fixed to the formation of a mineral form of calcium phosphates. Now, this happens in this case because we are relatively high pH conditions when the solubility of these calcium phosphate phases are very low, and because we have sufficient calcium in the water. And that's really characteristic of the regional, it's practically a characteristic of the regional geology and the water characteristics. Now, this basic principle have been used in treatment ponds in southern Florida. And there the issue was that you have the Everglades, which is a big national, it's a national park, but it's also a huge natural biodiversity hotspot. And it is bordered by sugarcane plantations. And sugarcane farmers use a lot of fertilizer, so there's a lot of phosphate and nitrogen that flows essentially from these fields into the Everglades and causes essentially eutrophication. So what is done is to have treatment ponds that are actually limed. So calcium carbonate ground up limestone is added to it, and the dissolution of that limestone then produces the calcium, and you can then actually fix the phosphate in a similar fashion. So potentially this could be a remediation technique applied to ponds that are in areas where the water does not contain naturally high calcium and high pH conditions. So I think that's certainly something to be explored. And that's where we learned that essentially a BMP, a best management practice that's used to deal with agricultural outflow, could be actually transported and used in the design of more effective ponds. So essentially reducing the the capacity to have this internal loading, essentially releasing phosphate that would then flow down the stream.
Excellent. Thank you. We have a few more minutes. Diego Costa, thanks for all the presentation. Hi, Philip. Has there been any progress in GWF in modeling carbon release from permafrost thawing?
Not directly. We're thinking about it. We're working actually on model developments to essentially take the soil processes part and look at DOC release. It's something that, let me tell you, there's a proposal that is being submitted that actually wants to specifically address that question. But right now, it's definitely a very important issue, and obviously, I think in a presentation that Puya gave about Julie, for instance, DOC dissolved organic carbon was mentioned as one of the problematic compounds or set of compounds in her case study. But yeah, the permafrost thaw, the DOC release, also the liability of this DOC is something that obviously a variety of people are working on, less so on the modeling side, I would say.
Thank you. Sorry that I'm going quite fast here. Youssef Laklidi, my question is indirectly related to Sherman's. Do your group have or follow a strategy to downscale and downscaling and upscaling in order to understand loads at different scale? Curious to know. So basically, it's scale dependency of the processes and the models.
Processes and the loads, yeah. Maybe Sarah, do you want to take a stab at that? Since you're thinking about upscaling the Ajax sewer shed up to a much larger geographical area.
Sure. Hello, everyone. Actually, that's a good question because most of the model has been developed or has been customized for just purpose, like for just certain regions and for a certain purpose. But what we are doing right now, we are thinking about generalization of what we have learned from these samples and these case studies that we have. So about the different species export and how to generalize them for like bigger models in different urban settings. And right now, like Mahyar mentioned, we have 3 samples in Richmond Hill, Ajax East and Ajax West, but our study area is much larger than that. We are going to cover 4 cities, Ajax, Pickering, Oshawa, and Whitby. And from these 3 small scales, we are going to come up with a generalization method that we can predict P export for those study areas as well. And also we are thinking about upscaling in like temporal upscaling, meaning that we are training our models and calibrating our models for current and historical data. But we are looking into projection for the future under different climate scenarios and different future scenarios like land covers probably. Yeah, I hope that I have answered your question, Youssef.
Yeah, Youssef says, thank you very much.
Thank you.
Thank you. Martin Clark says, hi, Philip. This was a really nice synthesis. Thank you for pulling it all together. So we are right at the top of the hour, 12 p.m. Central Time. I would like to thank everybody, the panelists here for presenting their work. It was a very nice setup, new to me. This is the last basically webinar of the webinar series of 2021-2022. We will come back to you next year, 2022-2023, the last basically GWF core modeling seminars, and we will send the invite. Meanwhile, I would like to sincerely thank everybody, all the presenters for the past webinars and everybody who helped for this series to be held. And finally, I like to again wish you a very happy summer. Enjoy the warm weather, and we will be coming back to you soon in September or October. So Philip, if you have to say something, please go ahead. Otherwise, we can call it a close.
I would also like to thank all our 3 Hqps who presented some of their work, and then also everyone who attended the presentations. And so also happy summer. It's starting to be summer here in Ontario, so we're looking forward to a nice, maybe not too hot summer, and then see everybody then at the fall webinar series.
Thank you very much.
Thank you all.
Have a nice day. Bye.
Take care, everybody.
Bye.